Okay, on example 2, use the Green's theorem to evaluate the line integral given. F is given 2D here, ing only, and the C is positively oriented, mean anti-clockwise direction, and the path is given. So as you can see, we have a closed curve, right, and anti-clockwise direction. So now we want to implement we can implement the Green's theorem, because we know that one is more simpler. So now we can have P equal to x squared y, and Q is given by x. So Py is x squared, and then Qx is 1. So now we want to find out the line integral along the curve C using Green's theorem. So Qx minus Py dA for the region R. So substitute Qx1 minus x squared dA. Okay, so now we based on the region provided, they only give us a point. Okay, so this is 1. So this is 1, 0, and this is 0, 0, and this is 1, 2. So in order for you to solve the double integral, you have to know the x and the y. You write the limit of x and the limit of y, and then meaning that you have the equation. You must have the equation of the line equation here. So how can we get the line? That is a linear equation. So you can use the formula of the construction of the linear equation. So we know that the general form is you can obtain the slope m. Okay, y equal to mx plus b, right? Okay, so now we can get the slope. You can get the slope using the point given. So the y divided by the x, so 2 minus 0 over 1 minus 0. So you get 2. So now you can have y equal to 2x plus b, and in order to get the b, you can use one of the point, whether 0, 0 or 1, 2. So now here we use the simplest one, the simplest point. So y0 x0 plus b, so b is equal to 0. So now the linear equation is 2x. So now in order to determine the limit, so here I'm using the x constant. So x 0 to 1, and then y is from 0 to x. Okay, so now we can put into our double integral 1 minus x squared dy dx 0 to 1, 0 to x. Okay, so first we integrate respect to y, so we only have y, and substitute the limit. So we have 1 minus x squared to x dx. Okay, so this one you have learned in method 2, right? The double integral. So then when we expand to x minus 2x cubed dx, then integrate, you have x squared minus 1 over 2 x4, 0 to 0 to 1. And when you substitute, you get 1 minus 1 over 2 and get half. So that is your solution. Okay. Okay, remember last time you can look at our previous example. So for the notes, it is stated as 5.7, but I don't remember which what is the name of the example that we have for this one. So maybe maybe I can check. Just a second. So the 5.7 revisited is in this, like the first notes for the line integral. So this one. So we have done this using a standard calculation of line integral where you have two curves here. When you have two curves, so the you have to compute the line integral for C1 and C2. When you total them up, and finally your total work done is 0. Okay, so now we want to as you can see here, how tedious your work, right? There are very many things that you have to provide if you use the standard calculation of the line integral. But now we want to use this example again by using Green's theorem, because why we can use the Green's theorem? Because we have the anti-clockwise direction and it is closed curve. Okay. So that is the thing that we want to read now. Okay. So we redraw. So we redraw. So let me copy the previous sketching. Okay, here I give a new name for this example. For Green's theorem, this is example 3. So this is, we have done this using a standard calculation of line integral. So we have the same now based on the instruction here, we have this particular curve, anti-clockwise direction and closed curve. So we want to determine the work done. So since we know that the work done is given by the line integral of f dot dr, okay, and it looks like since the requirement to apply the Green's theorem is applicable, so now we want to simplify our work by using the double integral qx minus py dA over the region R. So now this is your region. So the equation of this is coming from the equation of x squared plus 4y squared plus 4. Okay, so so now you have to, this is your P. So your P is y squared and your Q is 2y x plus 1. 2y x plus 1. So py is 2y and then qx. So when you expand 2yx plus 2y, so when you differentiate partially respect to x, you only have 2y. So when you substitute here, qx will give you 2y minus 2y dA, and you got integrand is 0, and when integrand is 0, and the answer is 0. Okay, and actually the f here is a force field. Sorry, the f given here is a conservative vector field. So as we know, if the curl f is 0, and actually this one is curl, the qx minus py is a curl onto the right, and your curl is 0. And since your curl is 0, so that's why your line integral here for the closed loop for conservative vector field, and if it is closed loop, and you will get 0 because your f here is conservative vector field. So meaning that in the exam, so if you are given a vector field and they ask you to evaluate some evaluate the line integral for some specific C. So the first thing that you must do is every time checking the conservative vector field, even though they don't ask for it, just to make sure that if it is conservative, then there are many things that you can be simplified. Okay, but if it is not, then you have to just back to the original standard, the standard calculation of doing the line integral. Okay, so the answer, the work done here is 0. Where the answer is the same as we discussed in the previous, which is example 4. Okay, so next example. Okay, work done again. So you are given to the vector field, which is a force field. So now you can see that they don't mention about the conservative vector field, and they don't mention about the Green's theorem, but you can check. So this one considered as example 4. Okay, example 4. So particle travel once around the circle. Okay, you have a circle counterclockwise. So definitely you can imagine. Okay, so you have a closed curve in anti-clockwise direction. Why explain? Radius 1 travel anti-clockwise. Okay, so then definitely you can use the Green's theorem. So P is EX minus Y cube. Q is cos Y plus X cube. Okay, so Py, you will get minus 3Y square, and then Qx, you will get 3x square. Then you want to calculate the work done. F dot dr over the curve C, and it is closed curve. So using the double integral, Qx minus Py dA, and Qx is 3x square plus 3y square dA. Okay, and it is not 0. So, and since your region is a circular region, so that is your R, then we can use the polar. Okay, so now we change into polar. 3r square r dr d theta. So your theta is 0 to 5, and your r is 0 to 1. So 3r cube dr d theta 0, 1 to 5. Okay, so then I'm sure that there is no problem here. Just a simple integration. You got 3. Okay, so then integrate r, so you got 3 over 4 r4 r 0 to 1 d theta, and you got 3 over 4 theta 0 to pi and you got 3/2 pi. Okay, so that is the total work done. Okay, so another example of the Green's theorem. So this consider as example 5. So your P, okay, so it is stated that it is already told you this is already mentioned that this is a closed curve. But okay, firstly you have to find out what is the shape of your path. Okay, so they are all a line segment starting at 0, 0, 0. So that is your initial point 0, 0. And then from 0, 0 to 1, 0, 1, this is 1, 0, 0, 0 to 1, 0, 1. You have to know how to read this. So from 0, 0 to 1, 0, from 1, 0 to 1, 2. This is 2. So this is 1, 2. And from 1, 2 to 0, 0, you have this. Okay, and now you can see that it is a closed curve back to the 0, 0 and anti-clockwise direction. So we can use the okay, we can have this particular region. Okay, so now your P is x minus 1 square. Q is there is y there. Okay, and x y minus 1 square. Okay, so in Py we will get x minus 1 square, and Qx you will get y minus 1 square. So your this one is actually f dot dr. So the f dot dr is given by the double integral qx is y minus 1 square minus x minus 1 square dA over the region. Okay, so it looks like you need to expand the given expression. So y square plus 1 minus 2y minus x square plus 1 minus 2x, and you will get y square plus 1 minus 2y minus x square minus 1 plus 2x. 1 cancel, so you have y square minus x square minus 2y plus 2x. Y square minus x square minus 2y plus 2x. Okay, so you want to have x constant, so dy dx. So here that is your to determine the limit. So x constant 0 to 1, but y you have to find the equation. So how to get the equation of y, the linear equation here. So find the m. So you have 2 minus 0 over 1 minus 0, so you got 2. So y equal to 2x plus b, and replace the point here, y0, x0, and you will get b equal to 0. So the equation that we obtain is y equal to 2x. So then you can determine the limit of y 0 to 2x. So 2 minus x, sorry, 2x. 2x, and then 1. So integrate respect to y. So 1 over 3 y cubed minus y x square minus y square 2xy. So y 0, y equal to 2x dx. So 1 over 3, 8x cubed minus 2x x square minus 2x square 2x minus 0. So when we simplify, you got 8 over 3 x cubed minus 2x cubed minus 4x square plus 4x square dx. So cancel. Am I correct? Just check it first. Okay, so replace y. So 2x x squared minus y, so 2x squared plus 2xy. So this becomes 8 over 3x cubed, 2x cubed minus 4x squared plus 4x squared. So this one cancel out. Only this one, when we simplify, we got 2 over 3. And then when we integrate respect to x, x4 over 4, and then simplify, you get 1 over 6. Okay, so that is your line integral result using Green's theorem. Okay, so that's all for Green's theorem. So normally, based on my experience, the Green's theorem is not so complicated. But the thing is, you have to understand there are some requirements for you to implement the Green's theorem. Okay. But in terms of calculation, you just apply the curve onto D, qx minus py, and just after that you have to apply the double integral, finding the limit of the region. Okay, you must shade the region. So this one should be, that is the region. It's like, okay. So that is all for the Green's theorem.